Hello there, and welcome to the Scientist Sleepy. Have you ever pondered what might lie at the very edge of existence, in places where the familiar rules of our universe seem to bend and break? Tonight, we embark on a gentle, quiet exploration into one of the cosmos's most profound and enigmatic phenomena, the physics of black holes. We will be delving into the heart of these celestial mysteries, seeking to understand the fundamental principles that govern these extraordinary objects, and perhaps, in doing so, find a deeper sense of perspective. So, if you haven't already, please allow yourself to settle in, find a comfortable position, and let the gentle rhythm of discovery begin. If you find this journey into the quiet wonder of the cosmos helpful, consider a gentle, no-pressure like or subscribe. It helps this sanctuary of calm continue to exist for those seeking a peaceful respite. And if you feel moved to, please share a single, simple word in the comments below. Perhaps a word that comes to mind as we begin to drift into the vastness of space. A word that reflects your current feeling, or a word that you associate with the profound mysteries we are about to explore. There is no right or wrong answer. It is simply an invitation to connect, a gentle whisper in the quiet. Now, let us turn our attention to the very fabric of reality, and the points where it is stretched to its absolute limit. The cosmic enigma beckons, drawing us to the very edge of comprehension. What truly lies beyond the event horizon, that boundary from which nothing, not even light, can escape? This is not a question of simple curiosity, but a profound inquiry into the nature of reality itself, a journey to the furthest reaches of our scientific understanding. For centuries, the concept of a black hole remained a theoretical curiosity, a mere mathematical consequence of Einstein's general theory of relativity. But as our observational capabilities have grown, these enigmatic objects have transitioned from the realm of abstract thought to tangible, albeit invisible, celestial bodies. The event horizon, often described as the point of no return, is not a physical surface in the way we understand a planet or a star. Instead, it is a boundary in space-time, a conceptual shell defined by the immense gravitational pull. Once an object, or even a beam of light, crosses this threshold, its fate is sealed. The very fabric of space-time is so drastically warped that all paths, all possible trajectories, lead inexorably towards the singularity at the center. Imagine a river flowing towards a waterfall. Upstream, you can still navigate, turn your boat and paddle away. But as you approach the edge, the current becomes too strong, the pull too great, and no amount of effort can divert your course from the inevitable plunge. The event horizon is precisely this ultimate waterfall of space-time. It is a one-way membrane, a cosmic barrier that separates our observable universe from whatever lies within its crushing embrace. The nature of what exists beyond this boundary is one of the most tantalizing and frustrating mysteries in astrophysics. Our current laws of physics, the very tools we use to understand the universe, break down at the singularity, the infinitely dense point at the heart of a black hole. We can describe the approach to the event horizon. We can observe the effects of its immense gravity on surrounding matter and light. But the true nature of the interior remains a profound enigma. It is a realm where our familiar notions of space and time are fundamentally altered, where the very concepts of cause and effect as we know them may cease to apply. The light that falls into a black hole carries information about the matter that formed it, but once it crosses the event horizon, that information appears to be lost to the outside universe. This leads to the infamous information paradox, a deep puzzle that challenges our understanding of quantum mechanics and gravity. Some theories suggest that information might be preserved in some exotic form, perhaps encoded on the event horizon itself, or released through the subtle process of Hawking radiation. Others propose that the information is truly lost, implying a fundamental incompleteness in our current physical models. The event horizon, therefore, is not just a physical boundary. It is also an epistemological one, marking the limit of our current knowledge. It is a place where the known universe ends and the profoundly unknown begins. The sheer gravitational force required to create such a boundary is staggering. For a stellar black hole, formed from the collapse of a massive star, this boundary can be only a few kilometers across. For supermassive black holes, found at the centers of galaxies, the event horizon can span billions of kilometers, larger than the orbit of Pluto. Yet, regardless of its size, the principle remains the same. Cross this invisible line, and you are forever on a path inward. The light that we detect from the vicinity of black holes, such as the swirling accretion disks of superheated gas, is actually light that has not yet crossed the event horizon, or light that has been bent and distorted by the black hole's gravity from further away. The black hole itself, by definition, emits no light. It is a perfect absorber, a cosmic drain from which nothing returns. The concept of an event horizon forces us to confront the possibility of regions of spacetime that are fundamentally inaccessible to us, places where the rules of the universe as we experience them may not hold. It is a reminder of the vastness and the mystery that still surrounds us, a silent testament to the limits of our current understanding. The enigma of what lies beyond the event horizon is a powerful testament to the universe's capacity for surprise, a silent question mark at the heart of the cosmos, inviting us to ponder the deepest secrets of existence. And so, the event horizon stands as a silent sentinel, a cosmic veil that guards the ultimate unknown, reminding us that even in the vast expanse of what we can observe, there are boundaries beyond which our current sight cannot reach, and within which the profound mysteries of existence may forever reside. Gravity's ultimate triumph, the singularity's embrace. At the very heart of a black hole, beyond the point of no return, lies a concept so profound it challenges our very understanding of existence: the singularity. Imagine, if you will, a point of infinite density, an infinitesimal speck where all the mass of the collapsed star, or even an entire galaxy, is compressed. This isn't just extreme gravity, it's gravity's ultimate, undeniable triumph. Here, the familiar laws of physics as we know them begin to unravel, to break down. Space and time, as we perceive them, cease to have meaning. It's a place where dimensions collapse and our conventional notions of here and now are rendered utterly irrelevant. The singularity is not a physical object in the way we understand objects in our everyday lives. It is more of a mathematical concept, a boundary of our current scientific comprehension, representing the absolute extreme of gravitational collapse. Scientists theorize that within this singularity, the curvature of spacetime becomes infinite. This means that the very fabric of the universe is bent so severely that it effectively folds in on itself. It's a point where the gravitational pull is so immense that it overwhelms all other forces, even the strong nuclear force that holds atoms together. Even light, the fastest thing in the universe, cannot escape its clutches, hence the very name black hole. The sheer concentration of mass within an infinitesimally small volume means that the gravitational field at this point is beyond comprehension. It's a place where our equations falter, where the smooth, continuous fabric of spacetime, as described by Einstein's theory of general relativity, gives way to a chaotic, undefined point. This breakdown of physics is not a sign of failure in our theories, but rather an indication of the extreme conditions at play, pointing towards the need for a more complete theory, perhaps one that elegantly unifies general relativity with quantum mechanics. The singularity is the ultimate expression of gravity's power, a place where matter is not just compressed, but utterly annihilated in its conventional form, existing in a state that is currently beyond our direct observation and complete theoretical grasp. It represents the most extreme manifestation of gravity we can currently conceive, a point where the universe pushes the boundaries of what is physically possible. The immense pressure and density at the singularity are so great that they are thought to warp spacetime to an infinite degree, creating a region where our familiar understanding of physics simply ceases to apply. It is the ultimate compression, the final destination of matter that succumbs to the relentless pull of a black hole. And in this ultimate compression, we find the deepest stillness, a quiet that echoes the vastness of the cosmos. Spacetime's fabric warped, the distortion of reality. The very stage upon which all of existence plays out, the interwoven tapestry of space and time known to us as spacetime, is not a rigid, unchanging backdrop. Instead, it is a dynamic, fluid entity capable of being bent, stretched, and indeed profoundly warped. Imagine, if you will, a vast, invisible sheet stretching out infinitely in all directions. This is our conceptual model of spacetime. Now place a heavy, dense object upon this sheet. What happens? The sheet dips, it curves, it forms a depression around the object. This, in essence, is what massive objects, and especially black holes, do to spacetime. They don't merely occupy space, they actively reshape it. The more massive an object, the greater its gravitational pull, and the more dramatically it warps the surrounding spacetime. A star, like our Sun, creates a gentle curvature. Planets orbit within these subtle dips, following the paths laid out by this warped geometry. But a black hole is an object of such extreme density, such unimaginable mass concentrated into an infinitesimally small point, that its warp is not a gentle dip, but a catastrophic abyss. The curvature of spacetime becomes so severe that it folds in upon itself, creating a region from which nothing, not even light, can escape. This warping is not a force acting asterisk upon asterisk spacetime, but rather a fundamental property asterisk of asterisk spacetime itself. Gravity, as understood by Einstein's theory of general relativity, is not a mysterious pull from a distance, but the manifestation of this geometric distortion. Objects are not being pulled by a force, they are following the contours of the warped spacetime. Think of a marble rolling on a curved surface. It doesn't move because a hand is pushing it, it moves because the surface itself guides its path. Similarly, planets orbit stars, and stars orbit the galactic center, not due to a direct pull, but because they are tracing the curves in spacetime created by these massive bodies. The closer you get to a black hole, the more extreme this warping becomes. The lines of space and time become so contorted that the very concepts of direction and duration begin to break down. For an observer far away, time near the black hole would appear to slow down dramatically. This phenomenon, known as gravitational time dilation, is a direct consequence of spacetime being warped. The deeper the gravitational well, the slower time flows. At the event horizon of a black hole, this effect becomes infinite from the perspective of a distant observer. The light emitted by an object falling into a black hole would appear to us to become redder and redder, and dimmer, eventually freezing at the horizon, never quite crossing it, yet never quite reaching us. This warping of spacetime is not just a theoretical curiosity. It has been experimentally verified. The bending of starlight around the sun during a solar eclipse, for instance, provided early evidence for Einstein's predictions. Gravitational lensing, where the light from distant galaxies is bent and magnified by the gravity of intervening massive objects, including black holes, is another powerful testament to this fundamental warping. The very structure of our universe, the paths of light, the orbits of celestial bodies, the flow of time itself, are all dictated by the intricate dance of mass and the resulting distortion of space-time. A black hole represents the ultimate expression of this distortion, a place where the fabric of reality is stretched to its breaking point, a testament to the profound and often counterintuitive nature of the cosmos. The bending of space-time around a black hole is the universe whispering secrets of its fundamental geometry, reminding us that reality itself is a malleable, magnificent canvas. Light cannot escape, the definition of a black hole. The defining characteristic, the very essence of what makes a black hole, is its absolute and inescapable gravitational pull. Imagine a place where the force of gravity has become so overwhelmingly dominant, so infinitely concentrated, that not even the fastest thing in the universe, light itself, can break free. This is not merely a strong gravitational field. It is a gravitational field so profound that it warps the very fabric of spacetime to such an extent that all paths, all trajectories, lead inward towards a point of no return. This boundary, this invisible threshold, is known as the event horizon. Once something crosses this line, it is irrevocably bound to the black hole. There is no turning back, no escape. Even if we were to send the most powerful rocket, equipped with the most advanced propulsion system imaginable, it would be utterly futile. The speed required to overcome the gravitational pull at the event horizon would need to exceed the speed of light, a feat that is fundamentally impossible according to the laws of physics as we understand them. Therefore, the event horizon serves as the ultimate cosmic boundary, a one-way membrane into the heart of darkness. It is not a physical surface you could touch or see in the conventional sense, but rather a conceptual boundary defined by the escape velocity. The escape velocity is the minimum speed an object needs to escape the gravitational influence of a celestial body. For Earth, this speed is about 11.2 kilometers per second. For a black hole at the event horizon, this escape velocity reaches and then surpasses the speed of light, approximately 299,792 kilometers per second. This means that anything, including light, that enters this region can no longer travel outwards. It is trapped. The size of this event horizon, and thus the size of the black hole, is determined by its mass. More massive black holes have larger event horizons. For a non-rotating, uncharged black hole, this radius is known as the Schwarzschild radius, named after the physicist Karl Schwarzschild, who first derived this solution to Einstein's field equations. This radius is directly proportional to the mass of the black hole. For a black hole with the mass of our Sun, the Schwarzschild radius would be a mere 3 kilometers. For a supermassive black hole at the center of a galaxy, which can have masses millions or even billions of times that of our Sun, the event horizon can span distances comparable to the size of our solar system. The inability of light to escape is what makes black holes black. We cannot see them directly because no light emanates from within their event horizons. Instead, We infer their presence by observing their effects on their surroundings. We see the way their immense gravity bends the light from stars behind them, creating distorted images, a phenomenon known as gravitational lensing. We observe the violent dance of matter being pulled into them, forming superheated accretion disks that emit intense radiation across the electromagnetic spectrum, from X-rays to radio waves. We detect the subtle, yet powerful, ripples in space-time gravitational waves that are generated when black holes collide. These indirect observations are the clues that allow us to map the unseen architecture of the universe, to understand these enigmatic objects that are defined by their ultimate silence, their absolute containment of light. The very concept of a black hole challenges our everyday intuition about space and time. It is a region where the familiar rules of physics bend and break, where gravity reigns supreme, dictating the fate of all matter and energy that ventures too close. The event horizon is not a barrier to be overcome, but a fundamental characteristic of the spacetime itself, a manifestation of gravity's ultimate power. It is the point beyond which our knowledge, and indeed light itself, cannot venture. The definition of a black hole is thus intrinsically tied to this one inescapable truth. The speed of light is no longer fast enough to escape its embrace. It is this ultimate capture, this absolute dominion over the fastest entity in the cosmos, that solidifies the black hole's place as one of the most profound and mysterious phenomena in the universe. The absence of emitted light is not a void, but a testament to gravity's absolute reign, a quiet monument to the limits of escape. In this realm where even light surrenders, we find a profound stillness, a quiet testament to the universe's most potent embrace, reminding us that some boundaries, once crossed, lead not to an end, but to a deeper, more fundamental reality. Stellar collapse, the birth of a stellar black hole. The grand cosmic ballet of stars, a spectacle of light and fusion, is not eternal for every celestial performer. For the most massive among them, their final act is not a gentle fading, but a cataclysmic implosion, a dramatic collapse that can give birth to one of the universe's most profound enigmas, the stellar black hole. This is a process driven by the relentless force of gravity, a force that, in the case of a sufficiently massive star, ultimately overwhelms all other energies. Imagine a star, billions of times more massive than our own sun, burning through its nuclear fuel. For eons, the outward pressure generated by nuclear fusion within its core has perfectly balanced the inward pull of its own immense gravity. This equilibrium is the very essence of a star's stable existence. However, when this fuel is exhausted, the fusion ceases. The outward pressure that once held the star aloft against its own gravitational embrace vanishes. In an instant, gravity seizes absolute control. The star's core, no longer supported by the outward push of fusion, begins to collapse in upon itself with unimaginable speed and force. This collapse is not a gentle descent. It is a violent implosion. The outer layers of the star, still possessing immense momentum, rush inward, colliding with the collapsing core. This collision can trigger a supernova, a titanic explosion that blasts the star's outer shell into the cosmos, seeding the interstellar medium with heavy elements forged in its fiery heart. But for the core itself, the story is different. If the remaining mass of the core is greater than approximately 3 times the mass of our Sun, a threshold known as the Tolman-Oppenheimer-Volkoff limit, then no known force in physics can halt its further collapse. Neutron degeneracy pressure, the force that supports neutron stars, is insufficient. The core continues to shrink, its density escalating to infinite levels, its volume shrinking to a point of zero size and infinite density, the singularity. This singularity, the ultimate endpoint of gravitational collapse, is the heart of the stellar black hole. All the mass of the collapsed core is compressed into this infinitesimal point. Around this singularity, a boundary forms, a point of no return. This is the event horizon, the defining characteristic of a black hole. Anything that crosses this boundary, be it light, matter, or information, is forever trapped within the black hole's gravitational well. The very fabric of spacetime is so severely distorted and curved in the vicinity of the singularity that all paths, even those of light, lead inward. The birth of a stellar black hole is a testament to gravity's ultimate power, a process where the very laws of physics, as we understand them, are pushed to their absolute limits, creating an object that bends light, warps time, and represents one of the most extreme environments in the observable universe. And in the silent, vast theater of the cosmos, the death of a giant star becomes the genesis of an unseen, yet profoundly powerful, entity that whispers of gravity's final, absolute decree. Supermassive giants, far larger than their stellar siblings, are the silent, colossal architects of galaxies, their immense gravity shaping the very structures we observe. These aren't mere specks of cosmic dust. They are behemoths residing at the heart of most, if not all, large galaxies, including our own Milky Way, where Sagittarius A reigns supreme, a supermassive black hole with a mass equivalent to about 4 million suns. The sheer scale is almost incomprehensible. Imagine a single object with the gravitational pull strong enough to influence the motion of billions of stars, holding an entire galaxy together. Their formation is still a subject of intense scientific inquiry, with several compelling theories. One suggests they grow from smaller seed, black holes, perhaps stellar remnants or collapses of massive gas clouds in the early universe, gradually accumulating mass by devouring surrounding gas, dust, and even entire stars over cosmic timescales. Another theory proposes that they might have formed directly from the collapse of enormous gas clouds in the nascent universe, bypassing the smaller seed stage altogether. Regardless of their exact origin, their presence is undeniable. They are not just passive inhabitants. They are active participants in galactic evolution. The material that spirals towards them, forming an accretion disk, heats up to incredible temperatures, emitting vast amounts of radiation across the electromagnetic spectrum. This outward radiation, along with powerful jets of plasma ejected from the vicinity of the black hole, can have a profound impact on their host galaxy. These energetic outflows can either fuel further star formation by compressing gas clouds, or conversely, they can heat or expel gas, effectively quenching star formation and shaping the galaxy's morphology. Think of them as cosmic regulators, balancing the forces of creation and destruction within their galactic domains. Their influence extends beyond just the matter directly falling into them. The gravitational field of a supermassive black hole dictates the orbits of stars in the galactic center, influencing the dynamics of the entire stellar population. They are the gravitational anchors, the central engines that drive much of the activity and evolution we witness in the grand tapestry of the cosmos. The very existence of galaxies, with their spiral arms, central bulges, and surrounding halos, is intimately tied to the presence and influence of these titanic entities. They are the unseen, yet fundamental, sculptors of the cosmic landscape, their silent gravitational command orchestrating the dance of stars and gas across billions of light years. Their immense power and influence are a testament to the extraordinary forces at play in the universe, forces that shape everything from the smallest atom to the grandest galactic structures. They are the silent sentinels at the core of cosmic cities, their presence defining the very essence and destiny of the galaxies they inhabit. In their silent, gravitational dominion, supermassive giants orchestrate the grand ballet of galactic existence, reminding us of the profound, unseen forces that shape our cosmic home. The accretion disk, where matter meets its fiery fate. Around many black holes, especially those actively feeding, we find a phenomenon of breathtaking beauty and intense power: the accretion disk. This isn't a solid object, but rather a swirling, flattened structure of gas, dust, and stellar debris that has been drawn in by the black hole's immense gravitational pull. Imagine a cosmic whirlpool, where everything that ventures too close is caught in a relentless spiral, spiraling inwards towards the ultimate unknown. These disks are not uniform. They are dynamic, chaotic environments where particles collide, heat up, and emit vast amounts of radiation across the electromagnetic spectrum. The process begins as matter, perhaps from a companion star or interstellar clouds, gets too near the black hole. Gravity, ever the dominant force, begins to exert its influence, pulling this matter towards the central object. But this matter doesn't fall straight in. Instead, due to the conservation of angular momentum, it starts to orbit. As more and more matter is captured, it forms a flattened disk. The inner regions of this disk are where the most dramatic transformations occur. Particles here are moving at incredible speeds, approaching a significant fraction of the speed of light. The friction caused by these high-velocity collisions between gas and dust particles generates immense amounts of heat. We're talking temperatures reaching millions, even billions of degrees Celsius. This extreme heat causes the matter to glow intensely, not just in visible light, but also in X-rays and other high-energy forms of radiation. This is why accretion disks are often referred to as engines of the universe, capable of outshining entire galaxies. The structure of an accretion disk is also fascinating. It's not a smooth, uniform layer. Instead, it's often described as being composed of multiple annuli, or rings, each with slightly different properties. Closer to the black hole, the matter is hotter, denser, and moving faster. Further out, it's cooler and less dense. The inner edge of the accretion disk is particularly important. It's not the event horizon itself, but a region just outside it known as the innermost stable circular orbit, or ISCO. Matter within the ISCO will inevitably plunge into the black hole. The radiation emitted from the accretion disk can be so powerful that it can influence its surroundings, pushing away gas and dust, and even affecting the evolution of the host galaxy. Some of the most energetic phenomena we observe in the universe, like quasars and active galactic nuclei, are powered by supermassive black holes with incredibly luminous accretion disks. The complexity of these disks is still a frontier of research. Astronomers use sophisticated telescopes to observe the radiation emitted from these disks, trying to unravel their intricate structures and understand the physical processes at play. They study the spectra of light to deduce the temperature, density, and composition of the disk. They also look for variations in brightness and patterns of emission that can reveal the dynamics of the infalling matter. The sheer amount of energy produced is staggering. For every kilogram of matter that falls into a black hole, an accretion disk can convert a significant percentage of its mass energy into radiation, far more efficiently than nuclear fusion in stars. This efficiency is a testament to the extreme nature of gravity near a black hole. The magnetic fields within the accretion disk also play a crucial role. They can channel the infalling matter, help dissipate energy, and even contribute to the launching of powerful jets of plasma that shoot out from the poles of some black holes, a topic we will explore in another chapter. Understanding accretion disks is key to understanding a wide range of astrophysical phenomena, from the formation of stars and galaxies to the most energetic events in the cosmos. They are cosmic furnaces, where matter is not just consumed, but transformed into light and energy, offering us a glimpse into the most extreme physics in the universe. The swirling dance of matter, heated to unimaginable temperatures, paints a picture of raw cosmic power, a testament to gravity's ultimate embrace. In the fiery embrace of the accretion disk, matter's journey culminates in a brilliant, radiant farewell, mirroring the intensity of our own fleeting moments against the vastness of eternity. Jets of pure energy, the outbursts of the abyss. The vastness of space, often perceived as a silent, ethereal expanse, is in reality a dynamic theater of immense forces. While black holes themselves are regions of profound darkness, their influence extends far beyond their insatiable gravitational pull. One of the most astonishing phenomena associated with active black holes is the ejection of powerful, collimated streams of plasma, known as relativistic jets. These jets, often stretching for millions of light years, are not merely byproducts of a black hole's existence, but rather a testament to the intricate interplay between gravity, magnetic fields, and the very fabric of space-time. To understand these cosmic fountains, we must delve into the complex processes occurring in the immediate vicinity of a black hole, particularly within its accretion disk. As matter spirals inwards towards the event horizon, it forms a superheated, flattened structure called an accretion disk. Within this disk, particles are accelerated to incredible speeds, and intense magnetic fields are generated. It is the interaction of these magnetic fields with the infalling plasma that is believed to be the primary mechanism for launching these energetic jets. Imagine the black hole as a cosmic engine, and the accretion disk as its fuel source. The magnetic field lines, twisted and amplified by the swirling matter, act like conduits, channeling energy and particles away from the black hole's maw. These field lines, anchored in the rotating disk, can become so intensely wound that they effectively pinch off and accelerate plasma at speeds approaching the speed of light. These jets are not uniform outflows. They are highly structured, often appearing as coherent beams. The exact mechanism by which this collimation occurs is still an active area of research, but it is thought that the magnetic fields play a crucial role in confining the plasma into these narrow streams, preventing them from dissipating into the surrounding space. The energy contained within these jets is staggering. They carry vast quantities of kinetic energy, capable of influencing the evolution of entire galaxies. When these jets interact with the interstellar medium, they can trigger star formation, heat gas, and even push back against the growth of their host galaxies. This feedback mechanism is a vital component in understanding the cosmic balance. The composition of these jets is primarily plasma, a state of matter where atoms are stripped of their electrons, resulting in a soup of charged particles, predominantly protons and electrons, but also potentially heavier ions. The pure energy aspect refers to the immense kinetic energy carried by these particles, moving at near-light speeds. The physics at play is incredibly complex, involving general relativity, magnetohydrodynamics, and particle physics. The sheer scale of these phenomena, the power they wield, and their ability to shape galactic landscapes are truly awe-inspiring. They are a vivid reminder that even in the deepest, darkest corners of the cosmos, there are forces of creation and expulsion at play, a cosmic breath exhaling energy outwards. The formation of these jets is intimately linked to the spin of the black hole. A rapidly rotating black hole can extract rotational energy from its own spacetime, a process known as the Blandford-Zeenagic mechanism. This energy can then be channeled into the magnetic fields and subsequently launched as jets. This suggests a profound connection between the black hole's intrinsic properties and its observable outflows. The precise details of how the magnetic field lines become so twisted and how they accelerate particles to relativistic speeds are still being unraveled through sophisticated computer simulations and observations. However, the general picture is one of a highly dynamic and energetic environment surrounding an active black hole, a place where gravity and magnetism conspire to produce some of the most spectacular displays in the universe. These jets are not just fleeting events. They can persist for millions of years, continuously feeding energy into the intergalactic medium. Their presence is a key indicator of an active galactic nucleus, AGN, a class of galaxies powered by supermassive black holes at their centers. The study of these jets provides invaluable insights into the fundamental physics of extreme environments and the large-scale structure of the universe. They are the universe's way of exhaling, a powerful testament to the energetic nature of cosmic evolution, a grand statement from the heart of darkness. The outward expulsion of energy from the abyss reminds us that even in the deepest voids, there is a profound and dynamic exchange, a cosmic sigh that shapes the universe around it. Hawking radiation suggests that black holes are not entirely black, but slowly emit a faint thermal radiation, gradually evaporating over unfathomable timescales. This profound concept, born from the intersection of general relativity and quantum mechanics, challenges our most fundamental understanding of these cosmic enigmas. Imagine, if you will, the very edge of a black hole, the event horizon, a boundary beyond which nothing, not even light, can escape. It is here, at this cosmic precipice, that the magic of quantum field theory begins to reveal its startling secrets. Quantum mechanics tells us that even in the vacuum of space, pairs of virtual particles and antiparticles are constantly popping into existence and annihilating each other in an instant. These are not real particles in the sense that they persist, but they are fleeting manifestations of energy, governed by the uncertainty principle. Now, consider what happens when such a virtual particle-antiparticle pair appears right at the event horizon. It is entirely possible, indeed probable, that one particle falls into the black hole while its partner escapes outwards. To an observer far away, it appears as though the black hole has emitted a particle. This escaping particle carries away a tiny amount of energy from the black hole. Because energy and mass are interchangeable, as described by Einstein's famous equation E equals mc2, this loss of energy translates into a loss of mass for the black hole. This process, repeated over an immeasurable span of time, means that black holes, contrary to their seemingly eternal nature, are actually slowly, infinitesimally evaporating. The rate of this evaporation is incredibly slow, especially for stellar mass or supermassive black holes. A black hole with the mass of our Sun would take an estimated 1067 years to evaporate completely, a timescale so vast it dwarfs the current age of the universe. For supermassive black holes at the centers of galaxies, This timescale is even longer, potentially exceeding 10,100 years. This radiation is known as Hawking radiation, named after the brilliant physicist Stephen Hawking, who first proposed this theory. The temperature of this radiation is inversely proportional to the mass of the black hole. Larger black holes are colder and radiate more slowly, while smaller black holes are hotter and radiate faster. This implies that if a black hole were to somehow shrink to a very small size, it would become incredibly hot and evaporate in a final, spectacular burst of energy. The discovery of Hawking radiation has profound implications for our understanding of cosmology and the ultimate fate of the universe. It suggests that black holes might not be eternal prisons of matter and energy, but rather transient phenomena that will eventually cease to exist. This concept also touches upon the famous black hole information paradox, which questions whether information that falls into a black hole is truly lost forever, or if it can be retrieved through this radiation. While the direct detection of Hawking radiation remains a monumental challenge due to its extreme faintness for astrophysical black holes, the theoretical framework it provides is one of the most significant advancements in modern physics, bridging the gap between the cosmic scale of gravity and the subatomic realm of quantum mechanics. It offers a glimpse into a universe where even the most formidable objects are subject to change, a constant, subtle dance of creation and dissolution. And so, even the deepest darkness is not truly immutable, but part of a slow, cosmic breath. Time dilation, the stretching of moments. As we approach the immense gravitational pull of a black hole, a peculiar and profound phenomenon begins to unfold, one that challenges our very perception of time itself. It's a concept born from the intricate tapestry of Einstein's theory of general relativity, a theory that paints a picture of gravity not as a force, but as a curvature in the fabric of space-time. Imagine space-time as a vast, invisible sheet. Massive objects like stars and planets create dips and curves in this sheet. A black hole, however, is an object of such extreme density and mass that it creates an almost bottomless well in this fabric. A well so deep that anything falling in, including light, can never escape its grasp. Now consider what happens to time in the presence of such profound gravitational influence. For an observer far away from the black hole, time appears to flow at its normal, familiar pace. Clocks tick at their usual rhythm, seconds and minutes pass as we expect them to. But for an observer venturing closer to the black hole, or for an object falling towards its event horizon, something extraordinary occurs. Time begins to slow down, relative to the distant observer. This is not a trick of perception, or a malfunction of clocks. It is a fundamental alteration of the very passage of time. The closer one gets to the black hole's immense gravitational field, the more pronounced this time dilation becomes. If an astronaut were to approach the event horizon of a black hole, and a companion remained safely distant, the astronaut's clock would appear to tick slower and slower to the companion. Their movements would seem to become sluggish, their actions drawn out, as if they were moving through an invisible, viscous medium. For the astronaut themselves, however, time would feel perfectly normal. They would not perceive any slowing down of their own internal clock or their own experience of the world. Their heart would beat at its usual pace. Their thoughts would flow at their accustomed speed. The difference in the passage of time is purely relative, a consequence of their differing positions within the gravitational field. As the astronaut gets infinitesimally close to the event horizon, the point of no return time dilation would become extreme. To the distant observer, it would appear as though the astronaut were almost frozen in time, their descent agonizingly slow, their image fading as the light from them struggles to escape the ever-increasing gravitational pull. The astronaut's clock, if it could be observed from afar, would seem to tick at an infinitesimally slow rate, approaching a standstill. Yet, from the astronaut's perspective, they would continue to fall towards the singularity, their journey through time, from their own frame of reference, potentially even concluding in a finite amount of their own subjective time. This stark contrast between the two observers highlights the relative nature of time, a concept deeply woven into the fabric of our universe. This stretching of moments is not confined to the extreme conditions near black holes. It's a phenomenon that occurs everywhere in the universe, albeit to a much lesser degree. Even here on Earth, the slight difference in gravitational pull between sea level and the top of a mountain causes a minuscule difference in the rate at which time passes. Satellites used for GPS navigation, for instance, must account for both the effects of time dilation due to their speed and the weaker gravitational field they experience compared to the Earth's surface. Without these relativistic corrections, GPS systems would quickly become inaccurate, demonstrating that these seemingly abstract cosmic principles have tangible, everyday consequences. The concept of time dilation near black holes, therefore, is a powerful reminder that our intuitive understanding of time, as a constant and universal flow, is an approximation that holds true only in our everyday experience. In the grand cosmic theater, governed by the laws of relativity, time is a dynamic and flexible entity, capable of stretching and bending under the immense influence of gravity. It's a testament to the universe's ability to surprise and to challenge our deepest assumptions about reality. And so, the passage of moments, so familiar to us, is in fact a malleable dimension, subtly warped by the presence of mass, a cosmic dance where time itself can slow to a crawl, reminding us of the profound interconnectedness of space, gravity, and our very experience of existence. Imagine a world, a planet, or even a star venturing too close to the immense gravitational pull of a black hole. It's a journey from which there is no return, and the very fabric of that celestial body will undergo a transformation so profound, so extreme. It has earned a rather unsettling, yet scientifically descriptive, moniker: spaghettification. This is not merely a poetic flourish. It is the direct consequence of tidal forces, amplified to an unimaginable degree by the black hole's insatiable gravity. When any object, be it a planet, a moon, or even a human, approaches a massive gravitational source, it experiences what we call tidal forces. These forces arise because gravity weakens with distance. The side of an object closer to the gravitational source is pulled more strongly than the side farther away. On Earth, we experience this daily with the tides of our oceans. The moon's gravity pulls more strongly on the side of Earth facing it, and less strongly on the opposite side, creating bulges in the water that manifest as high tides. Similarly, the sun exerts tidal forces on Earth, though they are weaker than the moon's due to its greater distance. These forces, while significant enough to shape our planet's oceans, are relatively gentle on our everyday scale. However, when we consider the extreme gravity of a black hole, these tidal forces are magnified exponentially. A black hole's gravitational pull is not uniform across an object approaching it. If an object, let's say a planet, were to get too close to a black hole, the gravitational pull on the side of the planet facing the black hole would be overwhelmingly stronger than the pull on the side facing away. This differential in gravitational force would begin to stretch the planet along the direction of the black hole. Imagine a rubber band being pulled from both ends, but with one end being pulled with immense, unyielding strength, while the other is held with comparatively little force. This stretching is not just a gentle elongation. The intense gravity would compress the planet in the perpendicular directions. The planet would be squeezed from the sides while being stretched from the top and bottom, much like a strand of spaghetti being pulled. This process, spaghettification, would tear apart the planet, atom by atom, molecule by molecule, reducing it to a long, thin stream of plasma and gas that would then be funneled into the black hole. The very structure that held the planet together, the electromagnetic forces between its atoms and the molecular bonds, would be overcome by the sheer power of the black hole's gravity. The point at which this dramatic transformation begins is known as the Roche limit, though for black holes, this concept takes on a more extreme form. For stellar mass black holes, the Roche limit is relatively close to the event horizon, meaning any object that crosses this boundary is destined for spaghettification. For supermassive black holes, however, the Roche limit can be much farther out. This means that an object might be stretched and torn apart before it even reaches the event horizon. The intensity of the tidal forces depends not only on the mass of the black hole, but also on its size. A smaller, denser black hole will exert more extreme tidal forces at a given distance than a larger, less dense one. The spaghettification process is a stark illustration of how gravity, in its most extreme manifestations, can utterly dominate and dismantle matter. It is a testament to the fundamental forces that govern our universe, and a chilling reminder of the power that lurks in the deepest cosmic abysses. This relentless stretching, this cosmic deconstruction, underscores the profound and often violent nature of the universe's most enigmatic objects. And so, the stretching begins, a cosmic ballet of destruction, where matter itself is unraveled by the inexorable grip of gravity, reminding us of the delicate balance of forces that shape existence. The Schwarzschild radius, a sphere of no return. Imagine a point in space, a place where gravity's grip becomes so absolute, so profound, that even the fastest traveler in the universe, light itself, can no longer escape its embrace. This boundary, this invisible threshold, is known as the Schwarzschild radius. It's not a physical surface you could touch, but rather a conceptual sphere, a point of no return defined by the mass contained within it. The more massive an object, the larger its Schwarzschild radius, and the more potent its gravitational pull becomes at that critical distance. For our Sun, if it were to somehow collapse to a point of infinite density, its Schwarzschild radius would be a mere 3 kilometers. For Earth, it would be less than a centimeter. This remarkable concept, derived from Albert Einstein's theory of general relativity, paints a vivid picture of gravity's ultimate power. It tells us that for any given mass, there exists a specific radius at which the escape velocity equals the speed of light. Once an object crosses this invisible boundary, it is irrevocably drawn inward, destined to meet its end at the singularity at the heart of the black hole. The Schwarzschild radius, therefore, serves as the black hole's defining characteristic, the very edge of its domain, the place where the known laws of physics as we understand them begin to warp and bend in ways that challenge our very perception of reality. It is a stark reminder that the universe holds forces so immense, so fundamentally different from our everyday experiences, that they can fundamentally alter the nature of space and time itself. Within this sphere, the fabric of space-time is so intensely curved that all possible paths, all trajectories, lead inexorably inward. Think of it like being caught in a waterfall where no matter how hard you swim, the current is always stronger, always pulling you downstream. The Schwarzschild radius is the point where the river of space-time becomes a torrent, and escape is no longer a possibility. This radius is not a fixed size. It's directly proportional to the mass of the object. A star that collapses to form a black hole will have a Schwarzschild radius determined by its original mass. A supermassive black hole at the center of a galaxy, containing millions or even billions of solar masses, will have a Schwarzschild radius that spans astronomical distances, encompassing entire solar systems. The mathematics behind the Schwarzschild radius are elegant, a testament to the predictive power of general relativity. It's derived from the Schwarzschild metric, a solution to Einstein's field equations that describes the gravitational field outside a non-rotating, uncharged spherical mass. The radius itself, often denoted as Rs$, is calculated with a simple formula. Rs equals 2gm/c2, where g is the gravitational constant, m is the mass of the object, and c is the speed of light. This formula, though seemingly straightforward, unlocks the secrets of how mass dictates the size of this ultimate gravitational trap. It's a constant reminder that the universe is governed by fundamental relationships, where even the most extreme phenomena can be described by precise mathematical principles. The Schwarzschild radius is more than just a number. It's a boundary that separates the observable universe from the ultimate mystery, a cosmic event horizon that draws us into contemplating the very nature of existence and the forces that shape it. And so, the Schwarzschild radius stands as a silent sentinel, a boundary where the universe's most profound power takes hold, reminding us that even light, the swiftest messenger, can be held captive by gravity's ultimate decree. The Event Horizon Telescope has allowed us to peer into the void. For centuries, black holes were theoretical constructs, mathematical curiosities born from the profound equations of Einstein's general relativity. They were imagined as regions of space-time where gravity is so intense that nothing, not even light, can escape. Yet, their very nature made them invisible, existing only in the realm of inference and indirect observation. We could detect their gravitational influence on surrounding matter, witness stars orbiting an unseen mass, or observe the searing glow of material being pulled into their depths, but the black hole itself, the heart of darkness, remained tantalizingly out of reach. This profound mystery fueled our scientific curiosity, pushing the boundaries of what we believed was observable. The challenge was immense. How do you image something that, by definition, does not emit or reflect light? It would be akin to trying to photograph a shadow cast by an object that is itself invisible. Traditional telescopes, no matter how powerful, were fundamentally limited by the very properties of the objects they sought to study. The concept of an event horizon, a boundary beyond which escape is impossible, meant that any direct visual evidence would have to come from observing the immediate vicinity of this boundary, a feat requiring unprecedented resolution and sensitivity. The idea of directly imaging a black hole, of capturing its silhouette against the light of its surroundings, was once confined to the realm of science fiction. But as our understanding of physics deepened and our technological capabilities advanced, this seemingly impossible dream began to transform into an ambitious scientific endeavor. The quest to see the unseeable, to bring the most enigmatic objects in the universe into the light of direct observation, sparked a revolution in astrophysics. It required a radical rethinking of how we observe the cosmos, a leap beyond the capabilities of any single instrument. The solution lay not in building a larger telescope, but in creating a telescope of unprecedented scale, a virtual instrument spanning continents. The Event Horizon Telescope, or EHT, is precisely this: a planet-sized observatory, a network of radio telescopes spread across the globe, working in unison to achieve the angular resolution necessary to resolve the event horizon of a black hole. This intricate collaboration, involving observatories from the Atacama Desert in Chile to the South Pole, and from Hawaii to Spain, harnesses the power of interferometry. By combining the data from these widely separated telescopes, scientists can simulate a single telescope with a diameter equivalent to the Earth's. This technique, known as Very Long Baseline Interferometry, VLBI, allows us to achieve resolutions far beyond what is possible with any individual dish. The signals captured by each telescope are precisely timed and combined, creating an incredibly detailed image. The process is complex, requiring the synchronization of atomic clocks at each site and the recording of vast amounts of data onto hard drives, which are then physically transported to central processing centers. There, supercomputers meticulously correlate the data, piecing together the faint radio waves that have traveled across the cosmos. The first major triumph of the EHT was the imaging of the supermassive black hole at the center of the galaxy Messier 87, M87. This colossal object, millions of times more massive than our Sun, provided the perfect target for this groundbreaking technology. The resulting image, released in 2019, was a landmark achievement, revealing a bright ring of emission surrounding a dark central region, the shadow of the black hole. This shadow, a consequence of the intense gravitational lensing and light bending near the event horizon, provided the first direct visual confirmation of a black hole's existence and its characteristic appearance. It was a moment of profound scientific discovery, a testament to human ingenuity and collaboration. The image was not simply a picture. It was a validation of decades of theoretical work and a powerful demonstration of our ability to probe the universe's most extreme environments. It showed us the silhouette of gravity's ultimate victory, a stark reminder of the immense forces at play in the cosmos. The EHT has since also imaged the supermassive black hole at the center of our own Milky Way galaxy, Sagittarius A. Each observation refines our understanding, offering new insights into the dynamics of accretion disks, the behavior of plasma in extreme gravitational fields, and the fundamental nature of space-time. The data collected by the EHT is not just about creating images. It's about testing the limits of Einstein's theory of general relativity in regimes of incredibly strong gravity. By observing the precise shape and size of the black hole's shadow, scientists can look for deviations from the predictions of general relativity, potentially opening doors to new physics. The ongoing work of the Event Horizon Telescope continues to push the boundaries of our observational capabilities, promising even more breathtaking discoveries as we continue to peer into the void, unraveling the mysteries of these cosmic enigmas. And in that captured silhouette, a profound stillness resides, a visual whisper of the universe's grandest secrets, inviting us to ponder the vastness that lies just beyond our reach. Gravitational lensing, the cosmic magnifying glass. Imagine, if you will, that the universe itself is not merely a vast, empty expanse, but a dynamic, fluid tapestry woven from the very fabric of space-time. And within this tapestry, massive objects like the colossal forms of black holes do not simply exist. They actively shape and bend the very pathways of light that traverse them. This is the essence of gravitational lensing, a phenomenon so profound it allows us to witness the distant cosmos as if through an invisible cosmic magnifying glass. When light from a distant galaxy or quasar journeys across unimaginable distances, it encounters the immense gravitational pull of an intervening object, perhaps a galaxy cluster, or indeed, a black hole. This gravitational field acts not as a barrier, but as a curved lens, subtly redirecting the light rays. Instead of traveling in a straight line, the light bends around the massive object, much like light passing through a glass lens. The greater the mass of the lensing object, the more pronounced this bending becomes. For a black hole, with its singularity of infinite density and overwhelming gravitational force, this bending is at its most extreme. The light, instead of passing by unimpeded, is drawn into a curved trajectory, following the contours of the warped space-time. This bending can cause the distant object to appear distorted, magnified, or even replicated into multiple images. We might see a single distant galaxy stretched into an arc, a perfect ring known as an Einstein ring, or even several distinct images of the same object, each appearing as if it were a separate entity. The light that reaches us has taken a longer, more circuitous route, guided by the gravitational well of the black hole. It's as if the black hole is not just a devourer of light, but a sculptor of cosmic vistas, bending the very rays of illumination to reveal hidden wonders. This effect allows astronomers to peer further into the universe than would otherwise be possible, to study galaxies that are too faint or too distant to be observed directly. The light, though bent, carries with it the story of its origin, and the gravitational lens acts as a cosmic storyteller, presenting that story in a new, often breathtaking, form. The distortions and multiple images are not errors. They are the signature of gravity's pervasive influence, a testament to the interconnectedness of mass and light across the vast cosmic stage. The very shape of the universe as we perceive it is a consequence of these invisible forces at play. It allows us to see not just what is there, but to infer what else might be hidden, its light subtly nudged and reshaped by the overwhelming power of gravity. The phenomenon of gravitational lensing, therefore, transforms black holes from mere points of darkness into cosmic architects, shaping our view of the universe and revealing its most distant secrets. It is a beautiful demonstration that even in the absence of direct vision, the universe reveals itself through the subtle, yet powerful, influence of gravity. And so, the warped pathways of light, guided by the immense gravity of unseen objects, paint a picture of the cosmos far grander and more intricate than a simple, direct gaze could ever reveal. We have seen how the immense gravity of black holes acts as a cosmic lens, bending and shaping the light that travels through space-time, allowing us to perceive distant galaxies and phenomena that would otherwise remain hidden from our view, transforming the darkness into a canvas for understanding. The information paradox, a quantum conundrum. At the heart of our understanding of black holes lies a profound puzzle, a clash between two of physics' most fundamental pillars, general relativity and quantum mechanics. This is the information paradox, a concept that suggests that when matter falls into a black hole, the unique information it carries might be irrevocably lost to the universe. General relativity, our most successful theory of gravity, describes black holes as regions of spacetime where gravity is so intense that nothing, not even light, can escape once it crosses the event horizon. From this perspective, anything that enters is destined to be crushed into a singularity, a point of infinite density at the center, and its original properties, its quantum state, its history, seem to vanish. However, quantum mechanics, the theory that governs the universe at its smallest scales, insists on a principle called unitarity. Unitarity dictates that information is never truly lost. It can be scrambled, transformed, or hidden, but it always exists in some form and can, in principle, be recovered. This is akin to burning a book. The words are destroyed, but the atoms and energy that made up the book still exist, and if we could meticulously track every single particle and photon, we could, in theory, reconstruct the original book. The paradox arises because black holes, as described by general relativity, appear to violate this fundamental quantum rule. Imagine throwing a quantum-entangled particle into a black hole. Its entangled partner remains outside. If the black hole evaporates entirely, as predicted by Stephen Hawking's theory of Hawking radiation, what happens to the information encoded in the state of that original particle? Hawking radiation, a slow leakage of particles from the event horizon, is thought to be thermal, meaning it carries very little information about what fell in. Much like the heat radiating from a glowing ember doesn't tell you the precise story of the wood that burned. If the black hole disappears completely, taking the information with it, then unitarity is broken. This is a deeply unsettling prospect for physicists, as it suggests a fundamental flaw in our current understanding of the universe. Scientists have proposed various solutions to this paradox. One idea is that information might be encoded in the Hawking radiation itself, perhaps in subtle correlations that are incredibly difficult to detect. Another possibility is that information is stored on the event horizon, like a holographic imprint, or that it is somehow transferred to another universe or dimension. Some theories suggest that the singularity might not be a point of infinite density, but rather a region governed by quantum gravity, a yet-to-be-discovered theory that unifies general relativity and quantum mechanics, where information could be preserved. The very existence of this paradox highlights the limitations of our current physical models and points towards the need for a more complete theory of quantum gravity, one that can reconcile the seemingly irreconcilable behaviors of the very large and the very small. It's a testament to the universe's enduring mysteries, a reminder that even in the face of such immense cosmic power, the fundamental rules of existence may hold true, albeit in ways we are still striving to comprehend. And so, the universe whispers its secrets, reminding us that even in the face of apparent obliteration, the threads of existence may be more resilient, more interconnected, than our current understanding can fully grasp. Wormholes, theoretical tunnels through spacetime, offer a glimpse into possibilities that stretch our imagination beyond the familiar confines of our universe. These hypothetical structures, often depicted as shortcuts connecting distant points in spacetime, are a fascinating consequence of Einstein's theory of general relativity. Imagine spacetime not as a flat, unchanging canvas, but as a dynamic, pliable fabric, capable of being bent, stretched, and even pierced. A wormhole, in this context, is akin to folding that fabric so that 2 points, which might be light years apart in conventional space, are brought into close proximity. The concept of a wormhole, also known as an Einstein-Rosen bridge, was first explored in the mid-20th century by physicists seeking to understand the mathematical implications of general relativity when applied to extreme gravitational conditions. It's important to emphasize that while the mathematics allows for their existence, the physical reality of wormholes remains purely theoretical. We have not yet observed any direct evidence of their presence. The idea is that a wormhole would possess two mouths, each located at a different point in space-time, and a throat connecting them. Traversing this throat could, in theory, allow for travel between these 2 points much faster than light could travel through normal space. However, the stability of such a theoretical structure presents a significant challenge. For a wormhole to remain open and traversable, it would likely require the presence of exotic matter, a hypothetical substance with negative mass-energy density. This exotic matter would exert a repulsive gravitational force, counteracting the natural tendency of spacetime to collapse and close off the wormhole's throat. Without this exotic matter, any such tunnel would likely pinch off and disappear almost instantaneously, making it impossible to pass through. The energy requirements for creating and maintaining a traversable wormhole are also astronomically high, far beyond anything we can currently conceive of generating. Furthermore, the nature of what lies at the other end of a wormhole is also a subject of intense speculation. It could connect to another region of our own universe, a different universe entirely, or even a different point in time, although the latter possibility raises complex causality paradoxes. The theoretical exploration of wormholes, however, is not merely an exercise in science fiction. It pushes the boundaries of our understanding of gravity, space-time, and the fundamental laws of physics. They serve as a powerful reminder of the universe's potential for complexity and wonder, suggesting that our current perception of reality might be just a small glimpse of a far grander and more interconnected cosmos. The very concept challenges our notions of distance and time, inviting us to ponder the extraordinary landscapes that might exist just beyond the veil of our current observational capabilities. Even as theoretical constructs, they fuel our curiosity and drive the quest for deeper knowledge, reminding us that the universe is a place of profound mystery and boundless possibility. The mathematical elegance that permits their existence hints at a deeper structure to reality, a scaffolding of spacetime that might, under precisely the right, albeit currently unattainable, conditions, offer pathways to the unimaginable. While the practical realization of wormhole travel remains firmly in the realm of hypothesis, their theoretical existence opens up a universe of thought experiments, pushing us to confront the limits of our physical laws and the vastness of the unknown. They are, in essence, conceptual bridges to the unimaginable, born from the elegant mathematics of gravity. The universe, in its infinite complexity, might hold hidden pathways, whispers of connections we are only beginning to theorize. Primordial black holes, echoes from the early universe, are theoretical celestial bodies that may have formed not from the collapse of stars, but from the extreme density fluctuations present in the universe's very first moments, mere fractions of a second after the Big Bang. Unlike stellar black holes, which require the immense gravitational pull of a massive star to overcome its internal pressure and collapse, or supermassive black holes, which grow over billions of years by accreting matter, primordial black holes are envisioned as direct relics of the universe's infancy. Imagine the nascent cosmos, a seething, incredibly dense soup of energy and elementary particles. In such an environment, it is theorized that regions of space could have been so extraordinarily compressed that they collapsed under their own gravity, bypassing the need for stellar evolution altogether. These initial conditions, where the universe was infinitesimally small and unbelievably dense, would have provided the perfect crucible for their formation. The concept of primordial black holes is rooted in the inflationary epoch, a period of rapid expansion that is believed to have occurred immediately after the Big Bang. During inflation, the universe expanded exponentially, stretching quantum fluctuations, tiny, random variations in energy density, to macroscopic scales. Some of these amplified fluctuations, if they were sufficiently large and concentrated, could have become dense enough to collapse into black holes. These hypothetical objects could have spanned a vast range of masses, from incredibly tiny, perhaps even smaller than an atom, to masses comparable to that of a large star or even more. The smallest of these primordial black holes would have evaporated almost immediately after their formation due to Hawking radiation, a phenomenon where black holes slowly lose mass by emitting particles. Larger ones, however, could have survived to the present day. The existence of primordial black holes remains a subject of intense scientific investigation and theoretical debate. They are not directly observed, but their potential presence is inferred through various cosmological and astrophysical signatures. For instance, they are considered a candidate for dark matter, the mysterious substance that makes up a significant portion of the universe's mass, but does not interact with light. If primordial black holes constitute a portion of this dark matter, their gravitational influence would be felt across the cosmos, affecting the rotation of galaxies and the formation of large-scale structures. Scientists are searching for evidence of primordial black holes by looking for their gravitational lensing effects on distant stars and galaxies, or by detecting the products of their evaporation if they are still decaying. The subtle distortions of light as it passes by these invisible objects could reveal their presence. Furthermore, the potential for primordial black holes to have played a role in the early formation of galaxies, or even the seeds of supermassive black holes at galactic centers, is another avenue of research. Their formation in the universe's infancy means they could have been present long before stars began to form, acting as gravitational anchors around which early matter could coalesce. The study of these hypothetical entities pushes the boundaries of our understanding of both quantum mechanics and general relativity, offering a glimpse into the extreme physics that govern the universe at its very genesis. They represent a profound connection to the universe's earliest, most energetic moments, a time when the fundamental forces of nature were at their most potent, and the fabric of reality was being woven. In these nascent moments, when the universe was a fiery, nascent seed, the potential for gravity's ultimate triumph lay dormant, waiting to sculpt the very architecture of existence from the raw energy of creation. The Schwarzschild black hole is the simplest theoretical model. Imagine, if you will, a universe where gravity has achieved its most profound and elegant victory. This is the realm of the Schwarzschild black hole, a concept born from the elegant mathematics of Albert Einstein's general relativity, refined by the brilliant insights of Karl Schwarzschild. It represents the most fundamental, the most stripped-down version of a black hole, a celestial object defined by just three intrinsic properties: its mass, its electric charge, and its angular momentum, or spin. For the Schwarzschild black hole, we simplify even further, considering a perfectly spherical, non-rotating object with no electric charge. It is, in essence, gravity's ultimate, unadorned expression. The defining characteristic of this theoretical construct is its boundary, known as the event horizon. This is not a physical surface in the way we might imagine the surface of a planet or a star. Instead, it is a conceptual boundary, a point of no return. Once anything, be it a particle of light, a cosmic dust grain, or even a hypothetical spaceship, crosses this invisible threshold, its fate is sealed. The gravitational pull becomes so immense, so overwhelmingly powerful, that escape is no longer a possibility, even for light, the fastest entity in the universe. The event horizon is the ultimate manifestation of gravity's dominion, a silent sentinel marking the edge of the observable universe. The radius of this event horizon is directly proportional to the black hole's mass, a relationship described by the Schwarzschild radius. For a black hole with the mass of our Sun, this radius would be a mere 3 kilometers. For a supermassive black hole at the center of a galaxy, with millions or billions of times the Sun's mass, this radius would extend across millions of kilometers. Within this radius, space-time itself is so dramatically warped that all paths lead inward, inexorably towards the singularity. The singularity, in this simplest model, is a point of infinite density and zero volume at the very center of the black hole. It is here that the laws of physics as we currently understand them break down, a testament to the extreme conditions that black holes represent. The Schwarzschild black hole, though a theoretical idealization, serves as a crucial cornerstone in our understanding of these enigmatic objects. It allows us to isolate the fundamental effects of gravity in its most extreme form, providing a baseline against which more complex black hole models, such as rotating Kerr black holes, can be understood. It is a stark reminder that the universe, in its grandest designs, often operates with a profound simplicity, a fundamental elegance that belies its immense power and complexity. It is in this simplified model that we first grasp the sheer, unyielding nature of gravity's ultimate triumph, a concept both terrifying and, in its own way, profoundly peaceful. In the quiet geometry of the Schwarzschild black hole, we witness gravity's ultimate, unadorned statement, a silent testament to the universe's capacity for profound, inescapable order, inviting a surrender to the cosmic flow. The Kerr black hole, rotation and its mysteries. The universe, in its vast and intricate tapestry, presents us with phenomena that stretch the very limits of our comprehension. And among these, the rotating black hole, or the Kerr black hole, stands as a particularly profound example of nature's elegant complexity. Unlike the simpler, idealized Schwarzschild black hole, which is defined solely by its mass and is perfectly spherical, the Kerr black hole introduces a new, fundamental characteristic: angular momentum. This rotation imbues the black hole with a dynamic and intricate structure, fundamentally altering the geometry of spacetime around it and presenting us with a universe of new and fascinating mysteries. Imagine a cosmic whirlpool, not of water, but of the very fabric of existence itself. This rotation is not merely an incidental detail. It is a defining feature that shapes the black hole's gravitational influence, its interaction with surrounding matter, and the very nature of the regions that lie just beyond its event horizon. The concept of a rotating black hole was first rigorously explored by the mathematician Roy Kerr in 1963, building upon the foundational work of Einstein's general relativity. His mathematical solutions revealed a universe far more nuanced than previously imagined, where the spin of a black hole creates a region known as the ergosphere, a zone where spacetime itself is dragged along with the black hole's rotation. Within the ergosphere, it is impossible to remain stationary. Any object, even light, must move with the black hole's spin. This is not a force in the conventional sense, but rather a consequence of spacetime being so profoundly distorted and twisted that it carries everything within it. The ergosphere is distinct from the event horizon, the boundary beyond which escape is impossible. The ergosphere lies asterisk outside the event horizon, and it is theoretically possible to enter the ergosphere and escape, provided one can harness enough energy to counteract the spacetime drag. This possibility opens up theoretical avenues for energy extraction from rotating black holes, a concept known as the Penrose process, where particles can be sent into the ergosphere split, and one part can fall into the black hole while the other escapes with more energy than the original particle possessed. This is a truly extraordinary idea, suggesting that these cosmic behemoths, often perceived as solely destructive forces, could also be sources of immense power. The shape of the Kerr black hole itself is also affected by its rotation. Instead of a perfect sphere, it becomes an oblate spheroid, flattened at the poles and bulging at the equator, much like a spinning planet. This deformation further influences the gravitational field, creating a more complex landscape for any unfortunate matter that ventures too close. The region where the singularity is located in a Kerr black hole is also a subject of much theoretical debate. In the Schwarzschild black hole, the singularity is thought to be a point of infinite density at the center. In the Kerr black hole, the singularity is predicted to be a ring, a toroidal shape, rather than a point. This ring singularity is a consequence of the black hole's rotation and further complicates our understanding of what lies at the very heart of these objects. The mathematics describing Kerr black holes are significantly more complex than those for Schwarzschild black holes, involving multiple parameters and intricate equations. This complexity reflects the richer physics at play when rotation is introduced. The existence of Kerr black holes is not merely a theoretical curiosity. It is widely believed that most, if not all, black holes formed from the collapse of massive stars will possess some degree of rotation. The angular momentum of the collapsing star is conserved, leading to a spinning black hole. Supermassive black holes at the centers of galaxies are also observed to be spinning, influencing the dynamics of gas and stars in their vicinity, and driving the powerful jets of plasma that are often observed emanating from them. The study of Kerr black holes pushes the boundaries of our understanding of gravity, spacetime, and quantum mechanics. They are laboratories for extreme physics, where our most fundamental theories are tested under the most demanding conditions. The mysteries of the ergosphere, the ring singularity, and the potential for energy extraction continue to inspire theoretical physicists and astronomers, drawing us deeper into the profound enigma of these celestial entities. The very existence of a rotating black hole reminds us that the universe is not a static canvas, but a dynamic, swirling vortex of energy and matter, where even the most seemingly immutable objects are in constant motion, shaping the cosmos in ways we are only beginning to comprehend. The spinning void, a cosmic dance of spacetime itself, reminds us that even in the absence of light, motion and mystery profoundly shape our universe. The Reissner-Nordstrom black hole is not merely a theoretical curiosity. It represents a fundamental expansion of our understanding of these cosmic entities, moving beyond the simplest models to incorporate an often overlooked property: electric charge. While stellar and supermassive black holes are generally thought to be electrically neutral, The Reissner-Nordström solution to Einstein's field equations allows for charged black holes. This concept, while perhaps less intuitive than the gravitational pull of mass, introduces a new layer of complexity and fascinating implications for the nature of spacetime and the very fabric of reality. Imagine, if you will, a black hole not just defined by its immense mass, but also by an electric field, a cosmic entity that simultaneously warps spacetime and repels or attracts other charged particles with a force comparable to its gravitational grip. This duality, this interplay of gravity and electromagnetism, opens up a universe of theoretical possibilities, pushing the boundaries of our comprehension of the universe's most enigmatic objects. The implications are profound, suggesting that even in the deepest voids of space, fundamental forces we experience every day on Earth continue to play a crucial, albeit perhaps subtle, role. It reminds us that the universe is a tapestry woven from many threads, and understanding its full beauty requires acknowledging the intricate interplay of all its constituent forces, even in the most extreme environments imaginable. The Reissner-Nordström black hole, a theoretical construct born from the elegant mathematics of general relativity, presents a stark departure from the simpler Schwarzschild black hole model. While the Schwarzschild solution describes a non-rotating, uncharged black hole, the Reissner-Nordström solution accounts for the presence of electric charge. This addition, seemingly minor, dramatically alters the structure and behavior of the black hole. The presence of charge introduces a second horizon, known as the Cauchy horizon, in addition to the event horizon. The event horizon remains the boundary beyond which nothing, not even light, can escape the black hole's gravitational pull. However, the Cauchy horizon is a more subtle boundary, a surface where predictability breaks down. If one were to cross the event horizon of a Reissner-Nordström black hole, they would encounter the Cauchy horizon before reaching the singularity. This second horizon introduces fascinating, albeit highly speculative, possibilities. Some theories suggest that crossing the Cauchy horizon might lead to a region of spacetime where causality is violated, or where one could potentially access other regions of the universe, or even other universes, through what are sometimes called wormholes. However, it's crucial to understand that these are highly theoretical concepts, and the existence of such phenomena is far from confirmed. The electric charge itself creates an outward electrostatic repulsion that counteracts some of the inward pull of gravity. This means that, for a given mass, a charged black hole would have a slightly larger event horizon than an uncharged one. The strength of this repulsion is determined by the amount of charge the black hole possesses. While most astrophysical black holes are expected to be electrically neutral, having shed their charge through interactions with surrounding plasma, the theoretical possibility of charged black holes allows scientists to explore a wider range of cosmic scenarios and test the limits of our physical theories. The mathematics behind the Reissner-Nordström black hole is complex, involving modifications to the spacetime metric that account for the electromagnetic field. This metric describes how distances and time are measured in the vicinity of the black hole, and the presence of charge warps this metric in a unique way. The singularity at the center of a Reissner-Nordström black hole is also theorized to be different from that of a Schwarzschild black hole, potentially being a ring singularity rather than a point singularity, especially if the black hole is also rotating, leading to the Kerr-Newman black hole, which combines rotation, charge, and mass. The implications of charged black holes extend to fundamental questions about quantum gravity, the unification of forces, and the ultimate fate of matter that falls into these extreme objects. They serve as a reminder that even seemingly simple gravitational objects can harbor profound complexities when we consider the full spectrum of physical forces at play in the cosmos. The very existence of these theoretical solutions forces us to confront the possibility that the universe might be far stranger and more intricate than our current observations can fully reveal, pushing the boundaries of our imagination and scientific inquiry. The concept of a charged black hole, while perhaps not directly observable in our immediate cosmic neighborhood, is a vital piece in the grand puzzle of understanding the universe's most extreme phenomena and the fundamental laws that govern them. It underscores the power of theoretical physics to explore realms beyond our direct experience, illuminating potential pathways for the universe's evolution and composition. The Reissner-Nordstrom black hole, with its dual horizons and electric charge, whispers of a universe where gravity and electromagnetism are not separate entities, but threads woven into a singular, intricate cosmic dance, reminding us that even in the deepest darkness, forces we understand can shape the very structure of existence, offering a glimpse into possibilities that stretch the limits of our current perception. Black hole mergers are cosmic collisions of immense power. When two black holes, these enigmatic entities of collapsed matter and warped spacetime, find themselves drawn together by the relentless pull of gravity, they embark on a celestial ballet that culminates in one of the most energetic events in the universe. This is not a gentle waltz. It is a cataclysmic embrace, a merging of two voids that reshapes the very fabric of reality. Imagine two celestial titans, each containing the mass of many suns, spiraling inwards towards each other. As they approach, their gravitational fields distort the surrounding space, bending light and stretching time in increasingly dramatic ways. The closer they get, the faster they orbit, their speeds approaching a significant fraction of the speed of light. This orbital dance is not only a visual spectacle, if one could witness it, but also a profoundly physical process. The black holes exchange gravitational influences, tugging and pulling at each other, their individual identities slowly dissolving as they become one. The forces at play are so extreme that they generate ripples in spacetime itself, disturbances that propagate outwards at the speed of light, carrying with them the imprint of this monumental event. These are gravitational waves, the faint whispers of cosmic collisions that have only recently become detectable by humanity, offering us a direct window into these otherwise invisible phenomena. The merger itself is a process of annihilation and creation. The smaller black hole, or perhaps both if they are of similar mass, is consumed by the larger one, or they coalesce into a single, more massive black hole. This new entity is not simply the sum of its parts. It is a transformed being, its properties dictated by the laws of physics that govern these extreme objects. The energy released during this process is staggering, far exceeding that of any supernova. It is a testament to the sheer power of gravity and the immense densities contained within black holes. The resulting gravitational waves are a direct consequence of the asymmetric way the two black holes interact and merge. As they spiral in, they are not perfectly aligned, and the final moments of their union involve a chaotic exchange of gravitational energy. This energy is radiated away as gravitational waves, carrying information about the masses, spins, and orbital orientations of the merging black holes. The detection of these waves by instruments like LIGO and Virgo has been revolutionary, confirming theoretical predictions and opening up a new era of astrophysics. We can now hear the universe in a way we never could before, listening to the echoes of black hole mergers and other violent cosmic events. The study of these mergers allows us to test the limits of Einstein's theory of general relativity in regimes of extreme gravity and high velocities, where its predictions are pushed to their absolute boundaries. It provides empirical data for understanding the dynamics of black hole populations, how they form, and how they evolve over cosmic timescales. We can infer the existence of binary black hole systems, understand the conditions that lead to their formation, and even begin to map the distribution of black holes across the universe. The power of these mergers is not just in the energy released, but in the profound insights they offer into the fundamental nature of gravity and space-time. They are cosmic laboratories where the most extreme physics unfolds, and in their wake, they leave behind a transformed universe and a wealth of new knowledge for us to ponder. The act of two black holes merging is a profound demonstration of nature's ability to transform energy and matter on the grandest scales, a process that, while violent, is an essential part of the cosmic evolution that shapes galaxies and the universe we inhabit. The universe orchestrates a symphony of destruction and rebirth, where even the deepest voids can, in their collision, send ripples of understanding across the vast expanse of existence. Gravitational waves are ripples in the fabric of spacetime itself, generated by the most violent and energetic cosmic events imaginable, and their detection has opened a new window into the universe, allowing us to hear the universe in ways previously thought impossible. These waves are not electromagnetic radiation, like light or radio waves, but rather distortions that propagate outwards from their source at the speed of light. Imagine spacetime as a vast, invisible ocean. When a massive object accelerates, particularly in a non-symmetrical way, it creates waves on this ocean, much like dropping a stone into water creates ripples. The sources of these gravitational waves are often the very phenomena we've been discussing, the cataclysmic collisions of black holes, the explosive deaths of massive stars in supernovae, and the merging of neutron stars. These events release an incredible amount of energy, and a tiny fraction of that energy is carried away by these gravitational waves. The concept of gravitational waves was first predicted by Albert Einstein in his general theory of relativity in 1916. He theorized that massive accelerating objects would warp the surrounding spacetime, and these warps would propagate outwards as waves. However, for decades, these waves were purely theoretical, incredibly elusive due to their minuscule amplitude. Detecting them requires instruments of unprecedented sensitivity. The most successful detectors to date, such as LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo, work by using lasers to measure incredibly tiny changes in the length of their arms. These observatories consist of two long, perpendicular arms, typically several kilometers in length. A laser beam is split and sent down each arm, reflecting off mirrors at the ends and returning to a central point. If a gravitational wave passes through, it momentarily stretches one arm while compressing the other, causing a minuscule shift in the interference pattern of the returning laser beams. This shift, though incredibly small, on the order of 1,000th of the diameter of a proton, is precisely what the detectors are designed to capture. The first direct detection of gravitational waves occurred in 2015, a monumental achievement that confirmed Einstein's prediction and ushered in a new era of astronomy. This initial detection, catalogued as GW150914, originated from the merger of two stellar-mass black holes, approximately 1.3 billion light-years away. The signal was a characteristic chirp, a rising frequency and amplitude as the two black holes spiraled inwards and coalesced into a single, more massive black hole. Since then, numerous other gravitational wave events have been detected, including the merger of neutron stars, GW 170817, which also produced electromagnetic radiation, allowing for multi-messenger astronomy, observing the same event through different cosmic messengers. The study of gravitational waves provides unique insights into the nature of gravity, the properties of black holes and neutron stars, and the evolution of the universe. It allows us to probe events that are otherwise invisible to traditional telescopes, offering a direct glimpse into the most extreme environments in the cosmos. These cosmic tremors, born from the most violent dances of celestial bodies, whisper tales of creation and destruction across the vast expanse of spacetime, reminding us of the dynamic and ever-changing tapestry of existence. The cosmic web, black holes as structural pillars. Our understanding of the universe has evolved dramatically, moving from a flat, static canvas to a dynamic, interconnected tapestry. For a long time, the dominant view of cosmic structure was one of isolated galaxies, scattered like islands in an infinite ocean. But as our observational capabilities sharpened and our theoretical models deepened, a more intricate and profound picture began to emerge: the cosmic web. This vast, filamentary network, stretching across billions of light-years, is not merely a passive distribution of matter, but an active, organizing principle. And at the very heart of this immense structure, playing a role far more significant than once imagined, are black holes, particularly their supermassive counterparts residing at the centers of galaxies. These cosmic behemoths, born from the gravitational collapse of matter, are not just passive observers of cosmic evolution. They are, in a very real sense, the structural pillars that help to shape and maintain this grand, cosmic architecture. Imagine the universe not as a random scattering, but as a colossal, three-dimensional spiderweb, where galaxies are the dewdrops clinging to the threads. These threads themselves are immense concentrations of dark matter, vast rivers of invisible substance that dictate where ordinary matter, and thus galaxies, will eventually congregate. And where do the most prominent knots in this web form? At the intersections of these dark matter filaments, where the gravitational pull is strongest. These are precisely the regions where supermassive black holes find their homes, nestled at the hearts of the galaxies that have coalesced around these gravitational wells. The sheer mass of these central black holes, often millions or even billions of times the mass of our Sun, exerts a profound influence on their immediate surroundings. But their impact extends far beyond their galactic confines. Through the energetic processes associated with their feeding, particularly the expulsion of powerful jets of plasma and radiation, supermassive black holes can regulate the growth of their host galaxies and, by extension, influence the distribution of matter on the largest scales. These jets can push gas out of galaxies, preventing it from cooling and forming new stars, thereby controlling the rate of galactic evolution. This feedback mechanism is crucial. Without it, galaxies might grow too large too quickly, and the cosmic web might not form the distinct, filamentary structure we observe. The energy injected by these active galactic nuclei, powered by the accretion of matter onto supermassive black holes, can heat the intergalactic medium, the diffuse gas that permeates the voids between galaxies. This heating helps to maintain the pressure balance within the cosmic web, preventing the filaments from collapsing too rapidly, and ensuring that the overall structure remains stable over cosmic timescales. In essence, these black holes act as cosmic regulators, their immense gravitational power and energetic outflows sculpting the very fabric of the universe on the grandest of scales. They are not merely endpoints of stellar evolution, but active participants in the ongoing construction and maintenance of the cosmic architecture. The intricate dance of matter falling into these gravitational pits, and the subsequent expulsion of energy, creates a dynamic equilibrium that underpins the existence of the cosmic web as we know it. The filaments of dark matter, guided by the subtle hand of gravity, draw galaxies together, and at the heart of these galactic gatherings, supermassive black holes exert their shaping influence, preventing runaway growth and maintaining the delicate balance that defines the universe's grand design. Their presence, though often hidden from direct view, is an essential component in the grand, cosmic ballet. The silent titans at galactic cores are the unseen architects, anchoring the universe's vast, luminous tapestry. Galactic evolution, the influence of supermassive cores. Supermassive black holes at the centers of galaxies play a profound role in their development and evolution. At the heart of nearly every large galaxy, including our own Milky Way, lies a supermassive black hole, a celestial behemoth with a mass millions, or even billions of times that of our Sun. These cosmic titans are not merely passive inhabitants of galactic centers. They are active participants in the grand, slow-motion ballet of galactic evolution. Their influence is far-reaching, shaping the very structure, growth, and stellar populations of the galaxies they reside within. The relationship between a galaxy and its central supermassive black hole is a deeply symbiotic one, a cosmic feedback loop where each influences the other over eons. When matter such as gas and dust falls towards a supermassive black hole, it doesn't plunge directly in. Instead, it forms an accretion disk, a swirling, superheated vortex of material. As this matter spirals inward, it generates immense amounts of energy through friction and gravitational forces. This energy is then often expelled outwards in powerful jets of plasma, traveling at near the speed of light, and in broader outflows of radiation. These energetic outflows, collectively known as active galactic nuclei, AGN feedback, have a dramatic impact on the surrounding galaxy. One of the most significant ways supermassive black holes influence galactic evolution is by regulating star formation. The intense radiation and powerful winds emanating from AGN can heat up or even blow away the cold molecular gas clouds that are the birthplaces of stars. This process can quench star formation in a galaxy, effectively shutting down the creation of new stars. This is particularly evident in massive elliptical galaxies, which tend to have very little ongoing star formation and are thought to have had their gas reservoirs depleted by the feedback from their central black holes early in their history. Without the fuel for new stars, the galaxy enters a quiescent phase, its stellar population aging and reddening over time. Conversely, in some cases, AGN feedback can also trigger star formation. The shock waves from these powerful outflows can compress gas clouds, leading to a burst of star birth. This can create a cycle where periods of intense star formation are followed by periods of quenching, leading to complex and dynamic galactic histories. The precise mechanism and outcome depend on a delicate balance of factors, including the mass of the black hole, the rate at which it is accreting matter, and the properties of the surrounding gas. Furthermore, supermassive black holes appear to co-evolve with their host galaxies. Observations have revealed a remarkable correlation between the mass of a supermassive black hole and the mass of the central bulge of its host galaxy, as well as the velocity dispersion of stars in that bulge. This suggests that the growth of the black hole and the growth of the galactic bulge are intricately linked, likely through the same feedback processes. It's as if the universe has a fundamental law that ensures these two components grow together, maintaining a delicate cosmic equilibrium. The study of these central engines and their impact on galactic evolution is a vibrant area of astrophysics. By observing galaxies at different distances, and therefore at different stages of cosmic history, astronomers can piece together the story of how galaxies form and evolve over billions of years. The intricate dance between a galaxy and its supermassive black hole is a testament to the interconnectedness of the universe, where even the darkest and most enigmatic objects can play a crucial role in shaping the luminous tapestry of the cosmos. The silent giants at galactic hearts orchestrate the birth and death of stars, weaving the grand narrative of cosmic structures. The search for exoplanets, worlds beyond our own solar system, has captivated humanity for decades. Traditionally, our methods for detecting these distant celestial bodies have relied on observing the light from their host stars. We look for the subtle dimming of a star as a planet passes in front of it, or the slight wobble a star exhibits as it's tugged by the gravitational influence of an orbiting planet. These techniques have yielded an incredible bounty of discoveries, revealing a universe teeming with diverse planetary systems. However, the realm of black holes presents a unique and fascinating challenge, and indeed an opportunity for exoplanet detection. While a black hole itself emits no light, its profound gravitational influence can shape its surroundings in ways that are observable, and in some cases, can betray the presence of orbiting companions. Consider a black hole that is not actively feeding on surrounding matter, a quiescent black hole. For a long time, it was thought that detecting planets around such objects would be virtually impossible, as there would be no bright star to observe. Yet, the universe is endlessly ingenious. Even around a dormant black hole, there can be stellar remnants, perhaps a neutron star or even a smaller, less massive star, that might have survived the cataclysmic events leading to the black hole's formation, or perhaps been captured later. These companion stars, though dimmer than our Sun, can still be observed. If a planet is orbiting such a companion star near a black hole, its presence can be inferred through the same techniques we use for planets around ordinary stars. The dimming of the companion star as the planet transits, or the subtle gravitational tugs on the companion star, can be measured. The proximity to the black hole, however, adds a layer of complexity and intrigue. The intense gravity of the black hole can subtly distort the light from the companion star, creating gravitational lensing effects that might need to be accounted for. Furthermore, the orbital dynamics of the system are not solely dictated by the companion star. The black hole's immense gravity plays a significant role, potentially influencing the planet's orbit in ways that can be detected through precise measurements of the companion star's motion. Another fascinating avenue for exoplanet detection around black holes involves the study of accretion disks. While we often associate accretion disks with the fiery, energetic phenomena of active black holes, even a quiescent black hole can possess a faint disk of gas and dust, perhaps remnants from its formation, or from occasional interactions with interstellar matter. If a planet were to exist within or near such a disk, its presence could influence the flow of material. A planet could create gaps or warps in the disk, or its gravitational pull might subtly alter the distribution of matter, leading to observable changes in the disk's brightness or structure. These subtle perturbations, though faint, can be detected by highly sensitive telescopes. Moreover, if a planet were to orbit a star that is itself being tidally disrupted by a black hole, the planet's own gravitational influence could leave an imprint on the debris stream, offering another potential clue to its existence. The extreme environment near a black hole, while seemingly hostile, actually provides unique observational signatures that, with careful analysis, can reveal the presence of worlds that might otherwise remain forever hidden. The subtle dance of gravity around a black hole, even in its quietest moments, can whisper secrets of hidden worlds, reminding us that even in the deepest darkness, life's potential may find a way to bloom. The physics of extreme environments, particularly those found near black holes, serves as nature's most profound laboratory for testing the very foundations of our understanding of the universe. These cosmic entities, with their immense gravitational fields and exotic properties, push our established physical laws to their absolute limits, and often beyond. Our current theories, primarily Einstein's theory of general relativity for gravity and quantum mechanics for the very small, have been remarkably successful in describing the universe under normal conditions. However, the conditions near a black hole, the crushing gravity, the intense energy densities, the warping of spacetime itself, are anything but normal. Here, these two titans of physics are forced to confront each other, and it is in this confrontation that we discover where our current models begin to falter, or indeed, where they reveal astonishing new truths. Consider, for instance, the event horizon itself. General relativity describes it as a boundary beyond which nothing, not even light, can escape. But what happens at the singularity, the theoretical point of infinite density at the heart of a black hole? General relativity breaks down there, predicting infinities that physicists generally interpret as signs that the theory is incomplete. This is where quantum mechanics, with its probabilistic nature and its ability to handle the very small, becomes crucial. Physicists hypothesize that a quantum theory of gravity is needed to truly understand the singularity. Such a theory, which remains elusive, would attempt to unify the large-scale structure of spacetime described by relativity with the granular, quantized nature of reality at its smallest scales. The extreme conditions near a black hole are precisely the kinds of environments where such a unified theory might manifest its effects. Furthermore, black holes are sites of incredible energy. As matter spirals into a black hole, it forms an accretion disk, heating up to millions of degrees and emitting vast amounts of radiation. This process is incredibly efficient, far more so than nuclear fusion in stars. Studying these accretion disks allows us to observe matter behaving under extreme gravitational and electromagnetic forces, providing insights into plasma physics and high-energy astrophysics that are impossible to replicate on Earth. The powerful jets of particles that are often ejected from the poles of rotating black holes are another testament to these extreme environments, carrying energy across vast cosmic distances and influencing the evolution of galaxies. Understanding the mechanisms behind these jets requires a deep dive into magnetohydrodynamics in regimes of extreme gravity and energy. The very existence of phenomena like Hawking radiation, a theoretical prediction that black holes are not entirely black but slowly emit particles and lose mass, is a testament to the interplay between general relativity and quantum field theory. This radiation arises from quantum fluctuations near the event horizon, demonstrating that even the seemingly immutable boundary of a black hole is subject to quantum processes. While the radiation is incredibly faint for stellar mass and supermassive black holes, its theoretical existence is a crucial piece of evidence for the need to reconcile our understanding of gravity with quantum mechanics. Observing or detecting such faint radiation would be a monumental achievement, providing direct experimental evidence for these exotic quantum effects in a strong gravitational field. Gravitational waves, the ripples in spacetime predicted by Einstein and first directly detected in 2015, offer another window into these extreme environments. The most powerful gravitational waves are generated by cataclysmic events such as the merger of two black holes or neutron stars. These events create spacetime distortions so violent that they propagate outwards, carrying information about the masses, spins, and dynamics of the merging objects. By studying these waves, we can directly probe the behavior of gravity in its most extreme manifestations, testing general relativity with unprecedented precision and potentially revealing deviations that could point towards new physics. The precise waveforms detected from these mergers can be compared with the predictions of general relativity, allowing scientists to verify or refine our understanding of how gravity operates under the most intense conditions imaginable. The study of black holes, therefore, is not merely about understanding these fascinating objects in isolation. It is about using them as cosmic test beds. They are the ultimate proving grounds for our most fundamental theories of physics. The challenges they present force us to confront the limitations of our current knowledge and inspire the development of new theoretical frameworks. Whether it's the singularity, the event horizon, or the energetic processes occurring around them, black holes are where the smooth fabric of spacetime meets the quantum fuzziness of reality, and where our deepest questions about the universe are most vividly illuminated. In these extreme cosmic environments, our most cherished theories are tested, revealing both their incredible strength and their ultimate boundaries, reminding us that the universe holds profound secrets yet to be unveiled. The unseen universe, the prevalence of black holes. Even as we peer into the heart of galaxies and chart the vastness between the stars, a significant portion of the universe remains stubbornly hidden from our direct gaze. Black holes, by their very nature, are masters of concealment. They absorb light, they warp spacetime, and they exist in regions of the cosmos that are often far from our observational reach. Yet, despite their elusive character, the evidence strongly suggests that black holes are not rare anomalies, but rather ubiquitous and fundamental components of the cosmic architecture. The sheer number of stars in our observable universe, estimated to be in the hundreds of sextillions, implies that the formation of stellar mass black holes, born from the violent deaths of massive stars, should be a common occurrence. For every star that reaches the end of its life cycle, if it possesses sufficient mass, a black hole is likely to be its final, silent testament. And then there are the supermassive black holes, the colossal entities residing at the centers of most, if not all, large galaxies. These galactic behemoths, millions or even billions of times the mass of our Sun, are not isolated curiosities. They are integral to the structure and evolution of their host galaxies. The Milky Way, our own cosmic home, harbors a supermassive black hole at its center, Sagittarius A*, a fact that has become increasingly clear through decades of meticulous observation of stellar orbits around this unseen gravitational anchor. The prevalence of these galactic nuclei suggests a deep connection between the growth of galaxies and the presence of their central black holes, a relationship that continues to be a vibrant area of scientific inquiry. Furthermore, theoretical models and observational hints suggest the existence of intermediate-mass black holes, bridging the gap between stellar and supermassive, and perhaps even the possibility of primordial black holes, remnants from the universe's earliest moments, scattered throughout the cosmos like invisible dust motes. The universe, it seems, is far more populated by these dark giants than we might initially imagine, their influence woven into the very fabric of cosmic structure and dynamism, even when they remain beyond the reach of our telescopes. The unseen universe, in essence, is likely teeming with these gravitational shadows, shaping galaxies, influencing stellar evolution, and playing a profound, albeit often invisible, role in the grand cosmic ballet. Their sheer abundance speaks to the fundamental processes that govern the universe, from the collapse of individual stars to the formation and evolution of entire galaxies. They are the silent architects, the invisible anchors, the unseen engines of cosmic change, reminding us that much of the universe's story is written in absence, in the places where light itself cannot tread, yet where immense power and influence reside. The prevalence of black holes, therefore, is not just a matter of counting. It is an insight into the very nature of cosmic evolution and structure, a testament to the powerful, often unseen forces that sculpt reality. The unseen universe, in its silent expanse, whispers of the profound prevalence of black holes, their unseen presence a testament to the fundamental forces that sculpt our existence. Beyond our understanding, the limits of current knowledge. Our current scientific understanding, while vast and ever-expanding, encounters profound limitations when we attempt to fully grasp the nature of black holes, particularly at their innermost depths. These cosmic titans represent frontiers of physics where our most cherished theories begin to falter and diverge. At the heart of a black hole, the singularity, our equations of general relativity predict an infinite density and a point of zero volume. This is not a physical reality we can directly observe or measure, but rather an indication that our current model of gravity breaks down under such extreme conditions. It signifies a point where the very fabric of spacetime, as described by Einstein, ceases to be a smooth, continuous entity, and instead becomes something entirely alien to our everyday experience. The singularity is a mathematical artifact that points towards the need for a more complete theory, one that can reconcile the seemingly irreconcilable realms of gravity and quantum mechanics. Furthermore, the event horizon, while a well-defined boundary in classical general relativity, presents its own set of enigmas when viewed through the lens of quantum physics. The famous information paradox, for instance, asks what happens to the quantum information of matter that falls into a black hole. According to quantum mechanics, information cannot be destroyed, yet the classical picture of a black hole suggests that everything that crosses the event horizon is lost forever. Stephen Hawking's groundbreaking work on Hawking radiation, the slow evaporation of black holes, suggests that they do emit particles, But whether these particles carry the lost information remains a subject of intense debate and research. This paradox highlights a deep tension between our two most successful theories of the universe: general relativity, which describes gravity and large-scale structures, and quantum mechanics, which governs the behavior of the very small. Black holes, by their very nature, are extreme environments where both theories must apply, and their interaction reveals the inadequacy of each theory in isolation. The very act of observing a black hole pushes the boundaries of our observational capabilities. We cannot directly see a black hole because it emits no light. Instead, we infer its presence and properties through its gravitational influence on surrounding matter and light. The Event Horizon Telescope, a remarkable feat of engineering and collaboration, has provided us with the first direct images of the shadow of a black hole, a testament to human ingenuity. Yet these images are still indirect glimpses, and the true nature of what lies within remains veiled. The immense distances and the extreme conditions involved mean that our probes and instruments are inherently limited in their ability to gather direct, detailed information from the immediate vicinity of a black hole. We are, in essence, studying the effects of a phenomenon rather than the phenomenon itself in its entirety. This inability to fully comprehend or observe the innermost workings of black holes is not a sign of failure, but rather a profound testament to the vastness of the cosmos and the current limitations of our scientific endeavors. It is in these moments of facing the unknown, where our current understanding falters, that true scientific progress is often born. These cosmic enigmas serve as powerful motivators, driving us to develop new theoretical frameworks, design more sensitive instruments, and expand the very limits of human knowledge. They remind us that the universe is far more complex and wondrous than we can currently imagine, and that there are still fundamental truths waiting to be uncovered. The edge of our understanding is not an endpoint, but a doorway to further exploration. And in this vast unknown, in the quiet hum of cosmic mystery, we find a profound stillness, a reminder that our perspective is but a fleeting moment in an ocean of cosmic unknowns. The philosophical black hole, metaphors for the unknown. Black holes, in their profound mystery, transcend the realm of pure physics to become potent philosophical touchstones, serving as metaphors for the unknown, the unknowable, and the profound depths of existence that lie just beyond our immediate comprehension. They are not merely astronomical objects. They are cosmic mirrors reflecting our deepest questions about reality, consciousness, and our place within the grand tapestry of the universe. When we contemplate a black hole, we are, in a sense, contemplating the limits of our own understanding, the edges of what we can perceive and articulate. The event horizon, that boundary beyond which no information can return, becomes a powerful symbol for the mysteries that life presents us with, those moments, experiences, or truths that we cannot fully grasp or explain, yet which undeniably shape us. This inability to see what lies within, to truly know the interior of a black hole, resonates with our human experience of encountering situations or concepts that defy logical dissection. We are often faced with life's events that, like a black hole, absorb our questions and leave us with a sense of profound wonder, and sometimes a quiet acceptance of what remains hidden. The very act of studying black holes, of sending probes and telescopes to observe their effects from a safe distance, mirrors our human endeavor to understand the world around us. We gather clues, we analyze the light that bends, the matter that swirls, the gravitational whispers, piecing together a narrative from indirect evidence. This is much like how we navigate our own lives, constructing meaning from the fragments of experience, the echoes of conversations, and the subtle shifts in our own inner landscapes. Black holes remind us that the universe is not entirely transparent, that there are phenomena that exist and exert influence even when they remain invisible to us. This can be a comforting thought, suggesting that perhaps there are aspects of our own inner lives, our own subconscious, or even the broader cosmic consciousness, that operate in ways we cannot directly observe but which are nonetheless real and influential. The concept of a singularity, a point of infinite density and zero volume, pushes the boundaries of our mathematical and conceptual frameworks. It represents a breakdown in our current models of physics, a place where our equations cease to provide coherent answers. Philosophically, this singularity can be seen as a representation of ultimate truth, or the ultimate mystery, a point of origin or dissolution that lies beyond our ability to articulate or even conceive. It challenges our desire for complete knowledge and encourages an embrace of the profound uncertainty that is inherent in existence. Furthermore, black holes, through their immense gravitational pull, shape the very structures of galaxies. They are not just destructive forces, they are architects of cosmic architecture. This duality, of immense power to consume and to create, to destroy and to organize, is a recurring theme in philosophical thought. It speaks to the paradoxical nature of existence, where creation and destruction are often intertwined, and where what appears to be an end can also be a beginning, albeit in a form we may not immediately recognize. The philosophical implications of black holes invite us to cultivate a sense of humility in the face of the vastness and complexity of the cosmos. They teach us that not all questions have immediate answers, and that sometimes the most profound understanding comes not from knowing, but from accepting and appreciating the mystery. They encourage a shift from a purely rational, analytical approach to existence to one that also embraces intuition, awe, and a quiet reverence for the forces that shape our reality, forces that are as vast and enigmatic as the black holes themselves. And so, in the silent, majestic expanse of the cosmos, the black hole stands not just as a physical marvel, but as a profound philosophical symbol, inviting us to contemplate the unknown within and without, and to find a quiet peace in the face of life's enduring mysteries. The gentle gravity, finding peace in cosmic immensity. The profound concept of a black hole, often perceived as a terrifying void, can also be understood as an embodiment of gravity's ultimate, serene expression. It is not a destructive force in its essence, but rather a manifestation of the universe's fundamental inclination towards equilibrium, a point where all forces converge into a state of absolute stillness. Imagine, if you will, the vast expanse of space-time, a canvas upon which the cosmic ballet unfolds. Within this canvas, matter and energy dance, propelled by the invisible currents of gravity. A black hole represents the culmination of this dance, a point of profound convergence, where the energetic movements cease, and a singular, immense stillness is achieved. This stillness, this absolute absence of outward motion, is not a void of emptiness but a profound presence of gravitational dominance. It is the universe at its most fundamental, stripped bare of all superficial complexities, revealing the pure, unadulterated essence of attraction. Consider the immense forces at play, the unimaginable density, the warping of light and time. Yet, from the perspective of an observer safely removed, the black hole exists as a point of perfect balance, a celestial body that has reached its ultimate gravitational destiny. It is a reminder that even in the most extreme manifestations of cosmic phenomena, there is an underlying order, a deep and abiding principle of balance. The gentle gravity of a black hole in its ultimate stillness offers a profound lesson that even in the face of overwhelming power, there can be a profound, quiet peace. It is a peace born not of action, but of absolute, serene presence, a testament to the universe's capacity for both dynamic energy and ultimate, tranquil resolution. This stillness, this gravitational embrace, whispers of an end to striving, a surrender to the fundamental forces that govern all existence, offering a silent, majestic promise of rest. Within this immense stillness, the very fabric of reality is stretched and molded by a force so potent it bends light and warps time. The black hole is not merely an object. It is a region of space-time where gravity's influence is absolute, a testament to the universe's fundamental laws. The singularity at its heart, a point of infinite density, is the ultimate expression of this gravitational power, a place where our current understanding of physics unravels, hinting at deeper, more profound truths yet to be discovered. But even at the edge of this cosmic abyss, at the event horizon, a boundary beyond which escape is impossible, there is a peculiar kind of stability. It is a boundary defined by a precise radius, the Schwarzschild radius, a spherical demarcation representing the point of no return. This radius is not a chaotic barrier, but a mathematically defined limit, a testament to the predictable and ordered nature of even the most extreme cosmic phenomena. The very existence of such a precise boundary underscores the idea that even in the face of overwhelming gravitational pull, there is an underlying order, a cosmic architecture that governs the universe's most enigmatic features. The accretion disk, the swirling maelstrom of gas and dust spiraling into the black hole, though a scene of incredible violence and energy, is itself a predictable dance, governed by the laws of fluid dynamics and gravity. The jets of plasma ejected from the poles of some black holes, while appearing as explosive outbursts, are also a consequence of these fundamental forces, channeling immense energy in a directed, almost elegant manner. These phenomena, though seemingly chaotic, are all part of a grand, cosmic symphony, orchestrated by the invisible hand of gravity. The black hole, in its entirety, is a grand experiment in physics, a natural laboratory where the limits of our understanding are tested and expanded. It is a reminder that the universe, in its vastness and complexity, operates according to elegant, albeit sometimes unfathomable, principles. The gentle gravity, in its ultimate stillness, invites us to contemplate the profound order that underlies all cosmic activity, a serene balance that extends even to the most powerful forces imaginable. This profound stillness, this ultimate gravitational embrace, is not a void of nothingness, but a profound state of being, a cosmic equilibrium that transcends our everyday perceptions of force and motion. It is the universe's ultimate expression of surrender, a quiet acknowledgement of the fundamental forces that shape existence. The gentle gravity of a black hole, in its serene dominance, serves as a philosophical anchor, a point of reference in the vast ocean of our thoughts and anxieties. It reminds us that even in the face of overwhelming power, there is an inherent order, a cosmic dance that, while sometimes appearing chaotic, is ultimately governed by predictable principles. The concept of the event horizon, a boundary beyond which no information can escape, can be viewed not as a point of despair, but as a symbol of ultimate peace, a place where all striving ceases and a profound stillness is achieved. It is the universe's way of saying that all things eventually find their resting place, their ultimate equilibrium. The black hole, therefore, is not a monster lurking in the cosmic darkness, but a celestial body that has achieved a state of perfect gravitational harmony. It is a testament to the universe's capacity for both immense power and profound tranquility. The gentle gravity of these cosmic giants in their silent majesty offers a comforting perspective on our own existence. It suggests that even amidst the turbulence of life, there is an underlying order, a cosmic rhythm that guides us towards a state of eventual peace. The very immensity of a black hole, its ability to consume light and matter, paradoxically offers a sense of calm, a reassurance that the universe, in its grandest designs, ultimately seeks balance and repose. Sleep well, good night. It is time to rest now. If you happen to still be awake, you can drift into the next chapter now. Our calm exploration has covered the profound physics of black holes, from the immense gravitational forces that define them to the theoretical possibilities of wormholes and the subtle whispers of Hawking radiation. We have journeyed through the birth of stellar remnants, the galactic influence of supermassive giants, and the very fabric of spacetime warped and stretched by their presence. We have glimpsed the event horizon, a boundary of no return, and considered the deep mysteries of the information paradox. Tonight, we have reviewed the principles of gravity's ultimate triumph, the mesmerizing dance of accretion disks, and the energetic outflows that paint the cosmos. We have seen how these enigmatic objects, though often perceived as places of destruction, are fundamental architects of the universe, shaping galaxies and influencing the evolution of stars. Their existence pushes the boundaries of our understanding, reminding us of the vastness and complexity of the cosmos. This gentle contemplation of black holes offers a unique perspective. Just as light is forever bound to their depths, perhaps our own anxieties and stresses can, in their own way, be contained, understood, and ultimately released. By acknowledging the immense, the unknown, and the seemingly inescapable, we can find a quiet wonder in our place within this grand, cosmic tapestry. The profound silence of the void, the immense power held in check, can serve as a profound metaphor for finding peace within ourselves. It is time to rest now. Allow the vastness of the universe to cradle you, the quiet hum of cosmic forces to lull you. Sleep well. If you happen to still be awake, you can drift into the next chapter now.